Hello there, wind energy students. Dr. John Schrage here, and we're going to be wrapping up this very short module about turbulence today by talking a little bit about the processes of observing turbulence. How would you actually make a observation of the turbulence that was affecting a location at a given time? Now, you would think that as important as turbulence is in meteorology and atmospheric sciences and engineering and aviation, that there would be some kind of instrument that can measure turbulence, some kind of turbulenceometer or something like that. But in practice, there is no such thing. In fact, the only way to get an actual measurement of turbulence is to compute some statistical properties of the flow itself. So whether we're going to be using descriptive statistics like the mean or the standard deviation of the wind, or whether we're going to do a full-blown time series analysis of the wind and do something like computing the power spectrum or related techniques like an FFT, we're going to need to have good statistics to describe the turbulence. There's no way to actually just to measure the turbulence itself. And in order to get these statistics, we're going to need data. We're going to need to have high quality, very high frequency observations of the wind speed, actually preferably all three components of the wind speed, the west to east, the south to north, and the vertical components of the flow. And, well, our traditional meteorological instruments are going to kind of fail us in that regard. I mean, the kinds of instruments that we have at an ordinary National Weather Service or Federal Aviation Administration weather station are not going to be sufficient to do the job. I mean, like, here's a cup anemometer with a wind vane. A perfectly normal thing that anybody can set up for a few bucks. A National Weather Service can spend a great deal of money on and keep well calibrated and stuff, all those kinds of things that we learned about back in the instruments lecture. But the truth of the matter is, for turbulence calculations, this is not going to be sufficient. The response time of this equipment is not going to be fast enough to respond to the small-scale eddies that are going to be passing it as part of the turbulent component of the flow. In the case of like a cup anemometer, the mechanism of the spinning cups themselves simply has too much inertia to respond to very small changes, on the order of like a meter per second or something like that, from like second to second in the wind. The little cups will not respond fast enough. They'll go faster than the real wind for a little while, and then when the wind accelerates, they'll go slower than the real wind. This simply is not going to be a sufficient instrument for such a thing. And the same is true of the wind direction. The little anemometer, the wind vane, takes a few moments to respond to the changes in the wind direction, and that's just not going to be fast enough to deal with these very high-frequency little eddies that are passing the anemometer and the wind vane under turbulent flow conditions. If you want to do this correctly, you're going to need something much faster, something with faster response times. And in general, this is done using a sonic anemometer. That's actually the same picture of a sonic anemometer that we used back in the instruments lecture, where you might remember there's like effectively a microphone and a receiver in the X and the Y and the Z directions that are relaying little pulses of actual sound back and forth. One emits and the other picks up the signal, and based on the speed of the wind in each component of the flow, we are able to determine, based on the time it took for the sound to travel from the speaker effectively to the microphone effectively, gives us the speed of the wind. And this has very, very fast response time. Sonic anemometers used at meteorological field research stations, like the ones that my research group we work with in Africa, typically have responses on the order of like 10 observations a second. Sometimes as much as like 20 observations per second. So these things can take enormous numbers of wind speed observations. As these eddies are coming by, they're going to see the small changes and not so small changes in the wind speed literally on the order of like tenths of a second, so that we can actually see the structure of all these little eddies as they go by. And you're going to need that kind of temporal information if you're going to be computing like the turbulence statistics of the atmosphere, like variance and power spectra and so on. You're going to need that if you're going to make some kind of meaningful understanding of the turbulent structure of the atmosphere at any given time. Now, I keep throwing out the kinds of terms that we saw in the second lecture in this module about describing turbulence, variance and standard deviation, or the more fancy terms like power spectra. But there is one little detail about those kinds of ways of describing turbulence, especially variance, that is a little bit problematic. It makes us wonder if that actually is the best way to describe turbulence. I mean, for example, here I have a typical time series of the wind. It's about, I don't know, an hour and 20 minutes of wind data. I have to admit I faked this. This is just an Excel spreadsheet of random numbers that have certain properties that I've set it up for. And you can see that like at the beginning of the period near 12 o'clock, the winds were lighter and the winds got stronger later in the period, closer to 1 o'clock in the afternoon. And so over the course of like this hour and a half or whatever, the winds have certainly accelerated. And well, if you actually take a look at the winds in like the first period of time from like maybe 12 to 12:15, 12:30, something like that, you'll see that the actual variability of the wind is not all that great. The standard deviation of the flow is low. If you like averaged over, say, from 12 to 12:15 and then over that period computed the standard deviation, it just wouldn't be all that big. The range over which the winds are varying is just not that great. On the other hand, if we went later in this period, more like 1300 to 1315 or something like that, towards the end of this graph here, if we took the average over that time period and then computed the standard deviation or the variance or whatever across that period, you'd find out that the standard deviation was high during that later period, because the range over which they're varying is getting bigger. And that's very, very typical. Our experience of working with observations of the wind is that in general that tends to be the case. It is often the case, maybe even most of the time the case, that the standard deviation of the wind gets higher the higher the mean speed of the wind. That isn't necessarily a turbulence thing. That's more a property of how fluids move, plus the response of the instruments and so on. That isn't necessarily the same thing as turbulence. That's a problem, because clearly the standard deviation of the flow in the early part of this diagram is very small compared to the standard deviation of the flow in the late part of the diagram. We need some way of saying that this later period, it isn't necessarily more turbulent, it may just be that the flow is stronger. Turns out there's a very simple statistic we can compute that tells us this, that gives us a measure of this. It's called the turbulence intensity, or TI. It's actually a pretty straightforward thing. It's just the ratio of the standard deviation of the flow in the west to east direction, sigma u, divided by the mean wind speed in that direction over that same period of time. So let's say over a 15-minute period or something like that, you compute the standard deviation of the u component of the wind and the average of the u component of the wind, and then just take the ratio of the two. And it becomes this unitless measure of how turbulent the flow is. Standard deviation has units of like meters per second, the U-bar has units of meters per second, and so on. So they end up having no units, they'll cancel each other out. And just a measure basically of like a fraction of, how much of the flow is being described by turbulence. It kind of, to use the right term from statistics, this idea of this measure of TI, or turbulence intensity, has normalized our value of the turbulence. And it takes into account, therefore, the changes in the mean speed of the wind. I can give you another example of how you would need to know something like this. But this idea that there's more variability the higher the average value is. And that's the stock market. Okay, back in the day, the stock market traded with the Dow in the range of, let's just say, it depends how far back you go, let's say 1500. Okay, that was the value of the stock market on the Dow Jones Industrial Average. And on any given day, the stock market might be up 2 points or down 2 points, and they would come in on the news at the end of the news and tell you, and today stocks are trading higher and the market was up 1.5 points or whatever. Well, today the stock market is trading much higher. At the time I'm recording this, it's at about 18,000, and day-to-day variability might be more like 100. The market was up 75 points. The Dow was down 113 points today. Does that mean the market is more variable, like where people are like more freaked out by the market and it's trading more violently? No, it's just the fact that the overall value of the market is higher. Okay, it still varies about the same percentage. The market has always traded from day to day with a variability of about 1%. Okay, it's just that when the Dow was at like 1500, that would be about a gain or a loss of like a point on any given day. Whereas now that the market is trading around 18,000, that might be as much as like, 100 points on any given day. I mean, whatever. Okay, I see. It isn't that the market's more volatile now, it's just the overall valuation is so much higher. TI is like that, but for turbulence. Just the greater the wind speed, we kind of normalized now the turbulence with respect to the wind speed. So TI, if TI is actually increasing, the actual part of the flow that is variable is increasing. The flow is becoming more turbulent. If TI is decreasing, the flow is becoming less turbulent. So, like for example, to go back to that diagram that I sort of faked right here, in this case, I actually faked this time series such that the value of TI is equal to about 0.25 throughout this whole time series. I actually, with my mad Excel skills, faked this time series with random numbers such that any given window of time, you average over about a 15-minute period of time, compute U bar, compute the standard deviation of U, you're going to get right around 0.25. Okay? This time series is not more turbulent over on the right side later than it is on the left side. Okay? But it could have been. I mean, I could have changed the values along the way, I just didn't. Alright, based on that information, let's answer a couple quick questions before we're done with this lecture. So the next 3 questions are all about another time series that I faked over here, where there are various periods with higher and lower averages and higher and lower standard deviations and so on. And in question 1, I'm asking about, see I got 3 different like 15-minute windows highlighted there. Which of those 3 periods there has the highest value of U bar on that diagram? Would it be A, B, C, or you can choose D, which means they're all about the same? Alright, make a choice from those 4 options and get a little feedback before you go on to the second and more difficult question.